So for this one, we are given a gamma distribution and asked to find, I believe this is a gamma 2 distribution, 2 beta distribution, and we're asked to find the maximum likelihood estimator of beta. So what is our first step always with finding maximum likelihood estimator? Yeah, so we need the likelihood function, which we get by taking the product of all of these marginal density functions for the xi's. They've got product from I equals 1 to n of f xi of xi given beta. And I'll just fill in the density function that we're given. So this is 1 over 2 beta cubed xi squared e to the, and I'm going to write this as exp, negative xi over beta. And then where do we go from here? It's just xi and negative xi. But there's something else that we can simplify here that is even easier. And what is that? Or a simplification that we can make, rather. And what do we do with it? Okay, so we're taking here the product across n different terms of this thing. So if we want to bring this to the outside of the product, what does it become? Well, we want to bring this 1 over 2 beta cubed out. And remember that we are taking the product across n different terms, n different factors, because we've got I is 1, I is 2, I is 3, all the way up to n. And so we have n copies of this thing out front here. And so I can write this as 1 over 2 to the n, beta to the 3n. And then I'll have the rest of my product. Does that make sense how I did that? Okay, and what other simplification can I do? I can't cancel an exponent. I'm not taking a logarithm yet. But there is a way that I can simplify this product over all of those exponentials. If I have the product of like e to the a times e to the b. What is this equal to? Mm-hmm. And so how do I use that property to simplify my exponential within this product here? Okay, so what I've got right now is like exponential of negative x1 over beta, exponential of negative x2 over beta, and so on up to n. And so how can I combine these? So we are we're taking the product of all of these exponentials, and so the powers then get added together. So what this will turn into is 1 over 2 to the n, beta to the 3n, product from I equals 1 to n of xi squared. That's just going to stay as it is. But then this exponential turns into the exponential of negative sum from I equals 1 to n of xi over beta. Does that make sense? No, this is an exponential. So this is just a notational thing, and we've seen it before, is that if I write exp of y, for instance, this is just equivalent to e to the y. It's just another way of writing that. But the reason I'm doing it this way here is because this is going to be very cumbersome to have written as like an actual exponent. So I put it in the exp function. Does that make sense? Okay. And so is there anything else that we can do to this likelihood function to simplify it? Yeah, so this is all that we can do before taking the log. So we'll move on to the logarithm of this. And we got that the log likelihood of beta given x, which is just the log of the likelihood function that we have right here, is equal to, if I take the logarithm of this thing, how does that start to break down? What can I separate it into? Okay, so I will, because I'm multiplying this times this times this, I can separate that up into the sum of log this plus log this plus log this. And so I will have log 1 over 2 to the n, beta to the 3n, plus log of the product from I equals 1 to n of xi squared and then I take the log of this thing, and what happens? Um, we can't do that, but I mean, not exactly that way, but I take the log of this. Remember that this is all an exponential here. So the log just makes that go away, and I have minus the sum of the xi's divided by beta. Does that make sense? Okay, and so now there's some more simplification that we can do here. And what will that be? Are you talking about how I got these terms? I'm not sure. I'm not sure what you're asking about. Okay, so remember that this thing here is one term that I'm multiplying. The one in parentheses in blue is another one. This one in parentheses in green is another one. So I have three things that I'm multiplying together. And we can break it down more than that later, but for now I have three things that I'm multiplying together. And I take the logarithm of that product of the three. That can be decomposed into the sum of the logarithms of the three, because log of a times b is equal to log a plus log b. And so that gives us what we have below here. Because I take the log of the first thing, log of the second thing, and then log of the third thing. And when I take the log of the third thing, the exponential goes away. So I might, I'll write it as in terms of the exponential, just to make it more obvious. Yes. Mm-hmm. So this is what I have here. Does this make sense? Okay. And so let's look at this first term now. What can I simplify here? Cancel the second term. I'm just looking at, with this right here, how do I simplify what I just circled? I can't bring it outside, but what I'll do here is I'll change the color of this to make it more obvious how this is breaking up. I can have this as log of 1 over 2 to the n plus log of 1 over beta to the 3n. So I split up that multiplication. And then this is really 2 to the negative n is the 1 over 2n. So I can write this as negative n times log of 2 plus or rather minus 3n log beta. Does that make sense? Okay. And now let's look at the second thing. Where do I go with this second one? That I have in the blue still. Or I'll put it in green. Is there anything I can do to this one? Yeah, I can put the 2 outside. And I'm also taking still a product of things inside of a logarithm. So I can change that to a sum. And I'll do that in 2 separate steps. So I'll take this product and turn it to a sum. So I have the sum of the log of xi squared. And then each of these, because I'm raising the xi to the second power, I can bring the 2 in front. And so I have plus 2 times the sum of the log xi's. Does that make sense? Okay. And then, this one should be a plus here still. But I have the log of exponential of negative sum xi over beta. What do I do to this one? I'm just going to cancel the log and the exponential. So log and exponential are inverses of each other. So those cancel, and I'm just left with the sum of xi's divided by beta. Does that make sense? Exactly. And so this is my this is my log likelihood function. And I'll change this back to the dark blue for all of it. Now where do I go from here if I'm looking for the maximum likelihood estimator of beta? They don't all have an end in this. This is all the simplification that we'll do to the log likelihood. But what do we need to do next to it? You said theta? Theta is the parameter, which in our case is beta. Theta is sort of the default symbol for a parameter, but this one we're looking at beta as our parameter. What do we do regarding beta? So if we're trying to maximize this with respect to beta, we need to differentiate. Go ahead. Yeah, first and second derivative. So we differentiate with respect to beta. And what do we get from this? Not just -3. It'll be -3n over beta because the derivative with respect to x of log of u, or here u is a function of x, is u prime over u. So differentiating this thing with respect to beta, we get -3n over beta. What about the next term? What is the derivative of this one with respect to beta? 0. Mm-hmm. And so then this last one, what is the derivative of this with respect to beta? Divide by 2. Well, we can write this as this is negative sum of x beta to the negative 1. And so using the power rule here, we multiply by negative 1, reduce that negative 1 to a negative 2. And so this will be plus the sum of the xi's divided by beta squared. Does this make sense? Yeah. So here in the log likelihood, beta has power negative 1. And so the power rule says that we take this, multiply by the power, which turns the negative out here into a positive, and then reduce the power of beta by 1. So it turns from a negative 1 to a negative 2. And so we get the sum of xi divided by beta squared as our result there. Does that make sense? Okay. So now, what do we do with this now that we have the derivative of the log likelihood? Yeah. Yeah. So we have the derivative of the log likelihood. Now, what do we need to do with it? Um, I don't think we need to factor it. What we need to do is set the derivative equal to 0 and solve for beta hat. So set derivative equal to 0, replace beta with beta hat, and solve for beta hat. And our result we're going to say that here negative 3n over beta hat plus the sum of the xi's over beta hat squared equals 0. I can add this term to both sides. And we have that the sum of xi's over beta hat squared is equal to 3n over beta hat. And now what's our next step? Solving for beta hat. I wouldn't say cancel, but don't think about theta here, because beta is theta essentially. We're not looking for like a separate theta. Theta just means the parameter, which in our case is beta. What we need to do is algebraically solve this equation for beta hat. So I'm just asking an algebra question. How do we solve this for beta hat? Okay, cross multiply by what? Yeah, I multiply both sides by beta hat squared, and I end up with sum of xi equal to 3n beta hat. And so what is beta hat? Okay, and I can write this as x bar over 3. And this is my maximum likelihood estimator. Well, I haven't technically shown it's the maximum yet. I know that there's a local extreme right here. So what do I need to do to show that it's actually the maximum likelihood estimator? Yes. All right, so this was our first derivative up here. We take the second derivative, and we can just go with beta hat from the start here. Actually, I'll write beta. What is the derivative of this thing up here? What is the derivative of the first derivative? Yeah, okay. So we can write it that way. Negative 3n beta to the negative first plus sum of xi is beta to the negative second. And then what's the derivative of that? We subtract from the powers. Negative 2 to this. So we'll have 3n over beta to the negative 2 because we multiply this thing by negative 1 because that's our power on beta. And then we change that negative 1 power to a negative 2 power. Oh, and sorry, this should be just a 2. I was mixing notation. So just a beta squared in the denominator. Does this make sense? Okay. Because the power is -1. Because remember that our power rule is that d dx of x to the a is a times x to the a minus 1. And here, well, it's at the same time, really. You're just taking, like, if I'm looking at, for instance, the derivative of beta to the negative first with respect to beta, I just bring that -1 out front, and then I have beta to the negative second. And I'm multiplying that thing by a -3n, and that gives us what's right here. Does that make sense? Okay. And so now we can yeah, that's the derivative of the first term. What's the derivative of the second term? -2 in front. Yeah. Greater to the negative third, and up top we have some of xi. And we want to know, and if I write like this, that should be positive. We want to know whether this thing is negative. And we will plug in beta hat for beta. And beta hat is x bar over 3. So this is 3n over x bar over 3 squared minus 2 times, I can write sum of xi's as nx bar over x bar over 3 cubed. This first one is going to be 27n over x bar squared. The next one is, we've got 3 cubed is 27 times 2 is 64. Or sorry, 54. 54n over x bar squared, because we have an x bar cubed up down there, an x bar up here. So we end up with x bar squared in the denominator. And this is equal to 27n, rather negative 27n over x bar squared. Is this positive, negative, or do we not know? It's negative because 27 is negative, n is positive, x bar squared is positive. So this is less than 0. And so beta hat equal to x bar over 3 is the maximum likelihood estimator for beta. Yes, this is what we just showed. Because we found that x bar over 3 is where the first derivative is equal to 0. And does this make sense? Okay. And now we want to know whether beta hat is a consistent estimator of beta. And what does it mean for an estimator to be consistent? No, it means that the estimator converges in probability to the actual value of the parameter. Or in other words, the limit as n approaches infinity of the probability that beta hat minus beta is, or that beta hat is within epsilon of beta. Any bound we pick for that difference, this probability is going to go to 1. And to show that an estimator is consistent, it is sufficient to show that its variance goes to 0. As n goes to infinity. And I'll write this as a list. And 2, that its expectation, or that it is asymptotically unbiased, which is to say that the expectation converges to the true value of the parameter. Does this make sense? Okay. So, and I'm actually going to switch the order of these, but unbiasedness first, because that's usually a bit easier to show. Okay, so let's start by showing whether this thing is asymptotically unbiased. So we want to know for any value of n, what is the expectation of beta hat? Oh, sorry, and this should not be n. This should be, I didn't write n up here, did I? Yeah, it should be 3, not n. What does this evaluate to? There's no theta. Um, Theta is not relevant to this. It doesn't come into this at all because theta is just our parameter. It's just a stand-in for whatever parameter we're talking about. And here we're talking about beta. So, and really right now we're talking about what is the expectation of x bar over 3. Well, there's something simpler that we can do to start with for this. I've got the expectation of x bar over 3. I can write this as 1/3 of the expectation of x bar. So that's just a matter of factoring out that coefficient 1/3. Okay, and now what? What is the expectation of x bar? I'm talking about the expectation. We have a theorem that tells us something about this. What does the law of large numbers tell us? So this is super important to remember, is that the expectation of x bar, if the expectation of x exists, the expectation of x bar is just equal to the expectation of x. Additionally, and we're going to use this later, the variance of x bar is equal to the variance of x divided by n. Does this make sense? Okay. So then the variance, or sorry, the expectation of x bar is the expectation of x. And this is something that we need to find. Unless you think you're allowed to just use the expectation of the gamma distribution without proof. So is the expectation of the gamma something that you've been given and just told to use? Or should we calculate it here? And it has expectation and variance as well. Okay. And what does it say is the expectation of x? Does it just give you the PDF or does it give you expectation variance as well? What's the mean for the gamma? Okay. And we're told that it follows a gamma distribution. We need to decide what parameters though. So comparing to the PDF here shown in your notes, we're told that this is a gamma distribution, so that makes it easier for us. But comparing to what you have in your notes, what are the parameters for your gamma distribution here? But for this particular one, what is, because beta is just beta, I'll tell you that. Because that's the thing that we're trying to find. What is alpha though? Because our density doesn't say alpha in it. Alpha is some particular number for this specific distribution that we're looking at right now. I'm asking you to look at the distribution that you're shown in question 1. Look at that density function and compare it to the gamma distribution that's in your table and tell me what you think the parameter value for alpha is. What number is alpha? It has to be, it's always bigger than 0. But looking at this specific density function that we're shown in question 1, I want to know what alpha is in this. We're given a gamma distribution. We're not told what alpha is, but we're shown the density so we can figure out alpha. I'll give you a hint that you should look at what power is beta raised to in that denominator there. Negative x over. I'm asking you what power is beta raised to. Our density function starts off with 1 over 2 times beta to the third. So looking at that, we have beta to the third in the denominator out front. What does that suggest about what alpha is? Yeah, that's fine. So your table says f of x given alpha and beta is equal to 1 over gamma of alpha, beta to the alpha, x to the alpha minus 1, e to the negative x over beta. And so we should be comparing what we see here to what we see here to figure out what is alpha. And if I look right here at the beta to the third, this thing that I just boxed in, this is beta to the alpha. So I know based on that alpha has to be 3. And similarly, if I look here, this is x to the second. That means that this is comparing it to our formula, it's x to the alpha minus 1. So alpha minus 1 is 2. And so alpha is 3. So I can say here that x follows a gamma 3 beta distribution. Does that make sense? X to the power of alpha minus 1. Because 3 minus 1 is 2. So we know now that X follows a gamma 3 beta distribution. And what does this tell us about the expectation of X? It's the same as the mean. So what is the mean of this distribution? Okay, and what is that for this particular one? Three beta. Okay. And then what does that tell us about the expectation of beta squared? I mean, sorry, not beta squared, beta hat. It's 1/3 expectation of X, like we wrote above. And we just said that the expectation of X is 3 beta. So this is 1/3 3 beta. The 3's cancel. And so this is beta. And thus, um, actually, yeah, okay, yeah, thus beta hat is unbiased for beta. Um, this won't affect any of the work that we did. I think that I might have misspoke before. That um, sorry, I'm checking that I didn't misspeak on the asymptotic lane biasness. Um, the I'll just change this to it is unbiased. Because I don't think that actually asymptotically unbiased is a strong enough condition, but this is here. So this is fine in any case. Okay, so we've shown that it's unbiased. Next, we want to show that the variance goes to 0 as n goes to infinity. And thus, we want to show variance goes to 0. So let's write the variance of x here. So, let's write the variance of beta hat. This is the variance of x bar over 3. And so how can I simplify that? So we're applying the property that a times the variance of x is equal to a squared times the variance of x. X bar over 3. So the 3 is going to get squared. So we'll have 1 over 9 variance of x bar. And how can I express the variance of x bar? No, because I just applied that. That's how I got the 1/9 variance of x bar. No, we can't do that. We'll apply what I have up here in red. That the variance of this is the variance of x divided by n. So this is equal to, I'll just write this as 1 over 9n variance of x. And what is the variance of x? look at your table for this. So we can get this from the table. Alpha beta squared. And what is that in this case? And what is alpha? 3, okay. So alpha is 3 beta squared. And so the variance of beta squared, or sorry, the variance of beta hat rather, is equal to 1/3 1 over 3n beta squared. And what can we say about this that's relevant to showing consistency? So I want to say here that it goes to 0 as n goes to infinity. And so what is my conclusion from this? A consistent estimator of theta, sorry, of beta. Do you have any questions about this? Okay. And next, we want the asymptotic distribution of beta hat. And what do we say for this? So looking at the asymptotic distribution, what theorem is relevant to us? What do you mean where to look? What do I mean by asymptotic distribution? So with asymptotic distribution, you will typically be making a statement about some transformation of your estimator following some sort of normal distribution. And so I'll state the central limit theorem here, which is very important to this. And this says that if x comes from a distribution or follows a distribution with mean mu and variance sigma squared, which is less than infinity, then the square root of n times x bar minus mu converges in distribution to a normal distribution with mean 0 and variance sigma squared. Does this make sense? Do I memorize it or understand it? Both. This is something very important to know. So you should memorize it if you don't recognize this. And so this tells us what the distribution of our sample mean is. And then okay, so do you understand convergence and distribution? Because that's part of the statement of the theorem here. Okay. So convergence and distribution, we say that a sequence of random variables converges in distribution to a variable x. Oh, and I should say here what the sequence is. So I'll refer to my sequence as x1, x2, up to xn, converges in distribution to a random variable x if the cumulative distribution functions converge to the cumulative distribution function of x for all x, all values of little x. So I'm saying here the limit, any x value I pick, the limit of the CDF evaluated at that value little x as as n increases is equal to the CDF x. And our notation for this is going to be that x n converges in distribution to x. And the vast majority of the time, you'll be using this with estimators. So we're talking about the sample mean, for instance. Technically, or maybe not technically, but the notation you'll often see is that we put a subscript n on the x bar to denote that this is the value of x bar for a sample of size n, and that as n increases, we're getting a different distribution for that sample mean. And we're saying that if we take the sample mean as a random variable, subtract off the population mean, multiply that by the square root of n, this gives us another random variable. It's sort of like forming a z-score. Not quite, because we've got the variance separately, but we're standardizing it in a way. This sequence of these transformed sample means is going to converge in distribution to a normal with mean 0 and variance sigma squared. And so this tells us that as we take larger samples, the distribution of our sample mean is going to approach this normal distribution, and we'll be able to describe what the variance of that distribution is relative to n. Does this make sense? Okay. And I will state here two important properties. One is that convergence in distribution implies convergence in probability. Wait, sorry, that's not correct. Convergence in probability implies convergence in distribution. Wait, sorry, I'm second guessing myself. Let me double check this. Okay, convergence in probability implies convergence in distribution. And convergence in distribution to a constant implies convergence in probability to that constant. So this first one is the more significant one, is that, in short, convergence in probability is a stronger condition than convergence in distribution. Does this make sense? Okay. And so now with this concept, we can talk about the central limit theorem. And with the central limit theorem, we say that if x comes from a distribution with this particular mean and this variance, then this transformed variable converges in distribution to a normal 0 sigma squared. The delta method allows us to make transformations of the sample mean and describe their asymptotic distribution. And one more comment on this is that we say this as the asymptotic distribution of x bar. So if you're asked for the asymptotic distribution, I would write something like this. Delta method, suppose that G is a G is a continuous function with, I want to say that the derivative of G at 0 cannot be 0. I'm going to check that though, just to make sure that I don't misstate the theorem. Oh, it's the G prime at theta. So, all right, this is G prime at mu is equal to anything besides 0 as our setup for this. Then this will allow us to describe the asymptotic distribution of G of x bar n. We'll say that the square root of n times G of x bar n minus G of mu converges in distribution to a normal with mean 0 and variance sigma squared times G prime of mu squared. Does this make sense? Mm-hmm. Actually, oh, I forgot. This should still satisfy the conditions of the central limit theorem. So I'm gonna state this a little bit differently in terms of just saying the asymptotic distribution. Well, one's the sample mean, one's the population mean. So here I'm just using theta in place of mu, and I'll use theta hat in place of x bar, just because this is the more formal statement of it. That is more generalizable. But if the central limit theorem applies, then theta hat can be x bar n, and theta can be mu. So this is what we're using here. We want to find the asymptotic distribution of beta hat. What should we find first, or what should we write first? Mm-hmm. No G yet, but we're using this thing. We're using the central limit theorem. Because first we need to find the asymptotic distribution of x bar. So by the central limit theorem, the square root of n times x bar n minus the expectation of x bar, or the population mean, which in our case is 3 beta, is convergent in distribution to normal, mean 0, and variance is 3 beta squared. So this is what we say about the asymptotic distribution of the sample mean. Now we want to work with, rather than just the sample mean, beta hat. And so now what do we do? we're going to apply the delta method. What should our function g be? Mm-hmm. So we'll use the delta method for this. And this is with g equal to g of x equal to 3x. We have that the square root of n times, or sorry, not 3x. This is 1/3 x over 3. That beta hat, because that's x bar over 3, minus this thing divided by 3 is just beta, converges in distribution to a normal with mean 0, and variance this thing times g prime is just 3. Sorry, it's just 1/3. So it's just this thing times 1/3. And that's just beta squared. And this is the asymptotic distribution of beta hat. Does that make sense? That was just the thing that I just erased was just a stray mark. That was not a prime. The prime is for looking at the g of theta. And actually this should be beta squared over 3. Yeah, because we square the 1/3. Because we're using the delta method, which has this thing here. And for that one, we need to look at the derivative of g. And for this one, it's just 1 over 3. So g prime evaluated at beta, or g prime evaluated at beta, rather, is still just going to be 1/3. And so we square that, we get 1/9, multiply by 3 beta squared, and we get 1/3 beta squared. Does that make sense? Okay. And then this is all for question 1. Do you want to stop here still, or do you want to, do you want to stop here, or do you want to continue for another 15 minutes? Because we can just do question 2 next time. Okay, so I will put this in the Google Doc. Do you want to meet again tomorrow? Okay. What time would you like? Okay. Bye, Yusuf. Have a good one.